So our second type of decay we're going to talk about now is beta decay. And there's going to be 3 forms of beta decay. Now, beta decay can be identified by the weird little bee with a long tail on it, okay? So this is going to be a sign that there's a beta decay. So the first thing we're going to look at is what is called regular beta decay. In regular beta decay, you have a neutron that changes itself into a proton, which then means we have this negative little particle that's got to leave the nucleus. So think of it like this. This is very simplistic, so don't think that this is exactly how it works, but it's just something for you to visualize. If you know a neutron's neutral, think about this being your neutron, where it's balanced out. So there's quarks that make up the protons and neutrons. And so let's think of it as balanced, like there's a positive and negative. Like I said, very simplistic. This is not exactly how it works, but I'm trying to get you a visual. If this neutron changes itself to a proton, we randomly have this negative particle that has got to get out of that nucleus. So what happens is that is your little beta particle, okay? So when we talk about beta decays, the mass does not change because all that's happening is you're actually changing a neutron to a proton, and since they both have a mass of 1 AMU, nothing's going to happen in terms of your mass. So let's look at it this way. We're going to go really simple. So let's say that we've got 3 protons, and then I'm going to do 1, 2, 3, 4 neutrons. So let's say now that this neutron right here, okay, is going to change to a proton. So in our next picture over here, we now have 1, 2, 3, 4 protons and only 3 neutrons. Okay, so the other piece that we have from this is that little beta particle. So he's going to have no mass, but he's going to have a negative charge. So this is what it looks like from a particle standpoint. Let's put it into actual problems. Carbon-14 is what is used for carbon dating, and it is known for beta decay. So in beta decay, we have one of those neutrons change itself over to a proton, so my proton number is going to go up 1. My mass stays the same. Element number 7 is nitrogen. Last thing, we see the release of this beta particle. In the last slide, you saw me write an E for electron, but in this slide, I'm showing it as the B with the long tail for beta particle. So in regular beta decay, notice your mass does not change. So 14 plus 0 is still 14. However, your element goes up by 1 since the neutron changed to a proton. 7 minus 1 equals 6. Both sides balance out. So this is regular beta decay. Let's now talk reverse beta decay. So reverse beta decay. In the case of reverse beta decay, a proton is going to turn itself into a neutron, and we have release of what is called a positron, which is kind of like a positive electron. And I know that sounds really odd, but think of it this way. Electrons have no mass, and so this is a particle with no mass, but it's a little positive charge, because if the proton went to neutral, we have this little positive piece that's got to go somewhere, hence your positron. So how this looks for a nuclear equation then is, let's take iodine 131. Iodine's number 53. Let's say it goes through a reverse beta decay. So the proton changes itself to a neutron. So the mass stays the same, but I lost a proton. I look at my periodic table, and number 52 is tellurinium. The last thing then is the release of that little positron. Both sides still match up. 131 plus 0 is 131. 53, 52 plus 1 is 53. So your reverse beta decay, your mass will stay the same, but your atomic number is going to go down by 1. Our last of the beta decays is called an electron capture. An electron capture is when a proton and an electron are captured from that inner ring. So you've got your nucleus, so here's your nucleus, you got your protons, you got your neutrons, and then you have all these electrons cruising around your electron cloud, and an electron is captured. A proton coming together with a electron is going to balance out and become a neutron. So in this case, we now get a neutron. The reactions for these, you can always tell it's electron capture because it's going to take place on what's called the reactant side. So we're going to take phosphorus 31 and we're going to electron capture. So no mass, negative electron, go the other side. The mass stays the same, but my proton and my electron come together and form a neutron, so I'm going to go down one proton, which takes me to silicon. 31 plus 0 is 31. 15 minus 1 is 14. So the biggest deal between your reverse and your electron capture is your electron capture takes place on the reactant side and your reverse does not. So these are the beta decays. Beta is stronger than alpha, it's more penetrating, and it takes a piece of aluminum foil or thin metal to block it. So more penetrating than the alpha decay. Last video is going to be your gamma decay.